All right, so this class, we're going to talk about acid and base. This is the first of many lessons focused strictly on acid and base, and this is the introduction class. So a lot of definitions will be talked about in this class. So first of all, we're going to start with what is acid and base, the definitions of acid base, and then the difference between strong acid and strong base strong acid and weak acid versus strong base versus weak base. And then an important concept called conjugate acid-base pair. And then finally, we're going to look at the K values, the K for acid and base equilibria. So first of all, can you identify an acid when you see one? Or a base when you see one? So I have 4 common substances, some of which you see on a daily basis. So let's do a little survey here. The first one, Coca-Cola. Do you think that is acidic or basic or neutral? Anyone?
Acidic?
Are you sure?
No.
No, I'm just messing with you. It is actually acidic. If you just think about the taste of Coca-Cola, right? It tastes very sour without the sugar, of course. If you add the sugar, you still have that soury, acidic taste to it. It is, in fact, an acid. The pH of Coca-Cola is around 3, and it has carbonic acid as well as phosphoric acid dissolved in the water. If you remove the sugar, it tastes terrible. That is sparkling water, acidic water, essentially. It tastes kind of sour and bitter. So that is quite a concentrated acid because at 2.5 pH is quite low. It's almost the same as your stomach acid. All right, coffee. What do you think?
Acidic.
Acidic? You sure about that?
Yeah.
Yeah.
Yeah, okay. I can't fool you. It is, in fact, an acid. Coffee may taste bitter, and you learn in grade 10 that base tastes bitter, but the acid is what's found in coffee. Coffee has a lot of substances inside, and some of which have acidic properties, which makes the whole thing acidic. If you test the pH of coffee, I don't know if you have, but if you dip some paper into coffee, and the pH paper should come out red. I actually plan on doing this in class, and I planned on bringing all of this stuff, but well, we can't have real class, so that's a shame. But coffee is acidic. Okay, and what about eggs? Well, I hear no answers because probably you guys don't know. I didn't know until I looked it up. Eggs are kind of interesting. They're basic. The pH of eggs, if you crack open an egg and just test the pH of the egg white, it's about 8. It's slightly basic. This is shocking because it's one of the few foods that are basic. Almost everything you eat are acidic. Just think about it. There's tomatoes, lemon, Coca-Cola, oranges, apples, grapes. Those are all acidic because they have a sour taste. Food in general is acidic because you have a lot of amino acids and proteins and DNA. Those are all acidic. Also, there's citric acid in a lot of fruits. But eggs are one of the few substances that we eat that is basic. I can't think of something else that's basic that we eat. Baking soda doesn't count. That's an ingredient. We don't just scoop it and eat it. So basic things we usually don't eat. But eggs, there are exceptions. All right, last one, blood. What is the pH of blood? Acidic or basic or neutral? Anyone? Okay, silence, I'm assuming you guys don't know. All right, so here's a little extra information that I want to share. The pH of blood is exactly 7.35. With a plus or minus of approximately 0.01 or 0.02, it shouldn't be greater than that. If you go to the hospital, if you're sick, you go to the hospital, they check a lot of vital signs. Like, for example, they can check your body temperature. They can check your blood glucose level. They can check your blood alcohol level. They can check your immune cells. So there are many things that a hospital can check, but what they never check is your blood pH. The reason for that is they don't have to check. They know for a fact that it is 7.35. It doesn't change. Okay, it's not subject to change. If it did change, it would be very obvious. You wouldn't be there in the hospital awake. If the blood pH changes by as little as 0.05, that leads to unconsciousness. Anything greater than that leads to death. So blood pH must be maintained at exactly that number. It is slightly basic and pretty much neutral, because there's really very little difference between 7 and 7.35. But when it comes to blood, it has to be very specific, that number. It's slightly basic, okay? So your blood is technically a base, a very low pH base. So this brings us to the question, what exactly is an acid and what is a base? Very often you find that in English, you know what something is, okay, because you've been seeing it, hearing it all your life, but when they ask you to define it, you're stuck. So what is the definition of an acid? You know what acids are when I present one to you, but can you define an acid to somebody that doesn't know what it is without referring to the pH? That's kind of difficult. And chemists have been puzzled by the definition of an acid until this dude, Svante Arrhenius, came up with a definition in the 1800s, I believe. So he said that an acid is a substance that produces hydrogen ions in solution. Okay, H+. This is a definition that you learned in grade 10, which is, to be honest, fairly good for the most part. It does explain a lot of properties and why certain substances are acids. So for example, HCl, hydrochloric acid, if you put this in water, the hydrogen will ionize and you would have H+ and Cl-. You have H+ in solution. Okay, that's what makes something acidic. If you drop your hands in an acid, it hurts because of the H+ ions. And similarly, a base, according to Arrhenius, is a substance that produces hydroxide, OH, in aqueous solution. Right? A base also is corrosive. If you put your hand in a base, that will also hurt. And what hurts you is the hydroxide. For example, sodium hydroxide. That dissolves, and the sodium and the hydroxide will break apart. You release a lot of OH ions, and that's what makes something basic. And so that's just a review of grade 10 definitions of acid and base. However, this is not a very good definition because it fails to explain all the acid and bases. This does not explain why compounds like ammonia, NH3, behave like a base. Okay, I'm sure most of you heard that ammonia is basic. In grade 10, when we show you the pH scale with pictures, on the right side of the pH scale, the basic side, one example that they give you is ammonia. That's a household product. It's a base. No one in grade 10 questioned why. Like when I taught this in grade 10, I just gave them that example. Ammonia is a base. Okay. And then we learn about the Arrhenius definition. It releases OH. Like, okay. No one put 2 and 2 together and asked, wait, NH3 doesn't have an OH. How can that release OH if it doesn't have one, right? Well, that's where the Arrhenius definition fails. We need to look at acid and base with the new definition. So here come Johannes Bronsted and Thomas Lowry. So together, they formed new definitions of acid-base. So we call them the Bronsted-Lowry definition. So according to Bronsted and Lowry, an acid is a proton donor. Okay? It donates a proton. You heard me right. I said proton, not electrons, protons. And we've been trying to hammer this idea home ever since you took chemistry, that electrons are responsible for chemical reactions. Protons and neutrons, they do nothing in the nucleus, right? They sit there. So all of a sudden in grade 12, I tell you that, oh no, acids release protons. You'd be like, what, how? Do you just rip a proton away from one of your nuclei and just throw it out there? If you actually think about it, what is a proton? A proton is a plus charge, right, in the nucleus. And then think about the hydrogen atom, H. A hydrogen atom has 1 proton and 1 electron. If you were to lose that electron, you would end up with just a proton. So a proton is our way of saying H plus, hydrogen ions. If you donate hydrogen ions, you are literally donating a proton. That's what we mean by that. You don't literally rip one from the nucleus, it's already there. So by the same token, a base will be a proton acceptor. Okay, acid donates a proton, base will take that proton. So this has nothing to do with hydroxide. Well, it has something to do with hydroxide, but not in the definition. So this can explain why ammonia is a base. All it has to do is take a proton and you're a base. So the hydrogen ion is the proton. And we also told you that the hydrogen ion is what makes something acidic. Well, we didn't tell you that this doesn't exist. H plus does not exist as H plus because this is highly unstable and reactive. It will react with water to form a hydronium ion, which is H3O plus. Right? You don't have free-flowing hydrogen ions just swimming. They will bond with water to make this structure. If you see the Vesper 3D structure, that is hydronium. That is basically NH3, except you have an oxygen, not a nitrogen. So that is our acid molecule, H3O plus, not H plus. Okay, just to be clear in grade 12, we have to be more precise now. So bronze to Lowry acid is an acid that will donate a proton, in other words, hydrogen, to another entity. So if you look at the first equation here, water plus HF. HF is hydrofluoric acid. That's the acid that donates the proton to the water. And in this case, water will accept that proton, and by accepting a proton, water is behaving like a base. And so hence water is a base in this equation. You will make H3O plus and F minus. If you look at the second equation, you have water and ammonia. NH3 in this case will accept a proton from water. So water donates a proton to ammonia, and by donating a proton, water is behaving like an acid in this situation. You will end up with OH minus because you lost a proton, and NH4. It's just NH3 with an additional proton. If you look carefully, you quickly conclude that, hey, hold on a second. Water seems to bat for both teams here. Right, how can you be on both sides? You're an acid and a base. In fact, that's correct. Water can be an acid and a base. So the most common acid in the world is water. The most common base in the world is also water. All right, so because of Bronsted-Lowry, we no longer have to assume that acid-base reactions occur in aqueous solutions. Because you can have gases that undergo neutralization, acid-base reaction. So you have NH3 plus HCl. Normally, we consider this to be synthesis. In fact, okay, it is synthesis. It's just that we can also call it an acid-base reaction because NH3 is a base, HCl is an acid. So what essentially happens is the HCl will donate a proton to the NH3. You have NH4 and Cl. This is an acid-base reaction. Okay, it's weird to think of it this way, but in grade 12, since we have a better theory of acid-base now, we have to consider this as an acid-base reaction, not simply a synthesis reaction. Okay. So I said that water can both accept a proton or donate a proton. And as a result, we have a special word for that. If you bat for both teams, if you will, if you behave like an acid and a base, you're called amphoteric or amphiprotic, whichever floats your boat. Amphoteric is the more commonly used word here. So these are substances that are able to donate or accept protons. So they could be acid and base. Water is not the only example. There are many examples of amphoteric compounds. As long as you have a hydrogen to donate and you can donate it, or you can take a hydrogen, then you're amphoteric. Okay, and water is just a common example. So water is the most common acid and the most common base. So do we have any questions so far about definitions of acid-base, what amphoteric is? Good. All right, so here is a really, really important concept, something that we will use continually throughout the unit. Consider this reaction. This is the general form of an equilibrium of an acid and water. HA, well, H stands for hydrogen. A is acid, the rest of the acid. So when you put this in water, the HA being an acid will, of course, donate that hydrogen to the water. Okay, and then water will take it and become H3O. So that's the base, right? Well, that's just the forward reaction. But we also have a reverse reaction. So in the forward reaction, HA is the acid. And it donates a proton to the base water, okay, which becomes H3O. But since this is equilibrium, you can also look at this in reverse. So in reverse, you would have A minus, a base, accepting a proton from H3O, which donates a proton, which is an acid. If you look at it in the reverse, then you have A minus as the base, H3O as the acid. And we call it conjugate base and conjugate acid. So HA, the acid, loses a hydrogen and becomes A minus, the conjugate base. So an acid will become the conjugate base after it reacts. Similarly, water being the base after it accepts a proton, so it went from being a base to being a conjugate acid. Now you're able to donate a proton, so you are by definition an acid. So acid will become a conjugate base, and base will become a conjugate acid. Does that make sense? All right, so H3O is the conjugate acid, and A minus is the conjugate base. So you're cool with the definition of conjugate acid and base. It's just an acid reacts and becomes conjugate base. Base reacts to become conjugate acid. So here we have a conjugate acid base pair. Okay, you can pair up. If you look at these two equations, A and B, in the first one you have HA in water. So that's a classic general formula for the equilibrium of acid in water. The HA loses hydrogen to become A minus. So the HA and the A minus, they're very similar to each other. They're basically the same thing, except that for the A minus, you're missing a hydrogen. You lack a proton. And they form a conjugate acid base pair. So the definition of that is two species that differ by just a proton. Okay, somebody is missing a proton. That's it. That's the only difference. And the water and the H3O, again, they're the same thing, except the H3O has one additional proton. They differ by one proton. The acid will have the extra proton, and the conjugate base will lack that proton. So same thing in B. B, the base, plus water. Well, the base would then take a hydrogen. You have HB. And then you have OH from the water. And the B and the HB, the conjugate acid base pairs. H2O and OH, again, the conjugate acid base pairs. They differ by one proton. It's like find your buddy. If I give you a bunch of animals, chickens and ducks, well, a chicken goes with a chicken, a duck goes with a duck. They're the same thing. Okay, HA goes with A because they're literally the same thing. H2O goes with H3O. Again, they're the same thing. So you should be able to recognize conjugate acid base pairs. So here's an exercise. I have this thing. Write the conjugate base for all of the acid listed. And recall that they differ by just a proton. So if you have an acid, the conjugate base should be missing a proton. So I'll give you like a minute, and then I'll take this up in 1 minute. All right, so we need the conjugate base for every acid listed on the left. We start with HCl, which is very simple. The conjugate base is when you lose that hydrogen, so you just have Cl. You have a negative charge now because you lose H+. So you lose a positive, you become negative. All right, so next one, that's sulfuric acid, H2SO4. You will lose a proton. Notice what I said. You will lose a proton. You lose one. You don't lose both. Okay, you lose one, so it has now HSO4 with the 1 minus because you only lost one proton, one H+. Okay, you can lose the second one, but that is two separate reactions. That is two acid ionization reactions. So you can take that HSO4, so that's the next question now. You can lose that proton and become SO4 2 minus. Then that will be the conjugate base. All right, and then NH4, the pattern is you would just lose a proton, so that becomes NH3. If you had a positive charge, now it's neutral. You drop the charge by 1. H3O, you have 3 hydrogens. The conjugate base will be H2O. You lose a hydrogen, and the plus charge become neutral. And then water can then donate a proton. H2O will become OH. Now you have a negative charge. So do you see the pattern? Everything on the right side has one less proton than the one on the left side. So any questions about this? All right, so let's identify conjugate acid-base pairs in a reaction. So I'll do example 1 with you, and then I'll have you do example 2. You have HF plus water, you have F minus and H3O. So identify the conjugate acid-base pairs. So find everything that is similar. So HF and F, they're very similar. They differ by a proton. And water and H3O, they differ by a proton. So I listed them out. So they must be conjugate acid-base pairs. So which one is the acid, which one is the base? Because HF loses a hydrogen, that's the acid, and it becomes the conjugate base. Water gained a proton. So that's the base. And it becomes the conjugate acid. So there I have it. I finished the question. Identify the conjugate acid-base pairs. There we go. HF is the acid, F is the conjugate base. H2O is the base, H3O is the conjugate acid. Okay? Now, this is an equilibrium. The way I'm looking at this now is I look at it from left to right. Okay? I don't have to look at it that way. It's arbitrary. It goes in both directions. So if you look at this in reverse, it is equally valid. You can start from the right side. Why not? F becomes HF, so it gained a proton. And then H3O became H2O, it lost a proton. So because F gained a proton, it is the base, it's a proton acceptor. And the conjugate is HF, that's the conjugate acid. H3O is able to donate protons, so you're an acid, and you become the conjugate base. Look, they're different. But they're equally right. They're equally valid because it depends on your point of view. Okay, you can go from left to right or right to left, you get the same thing. Notice that HF is an acid on the left side. HF is the conjugate acid on the right side. The only difference is you add the word conjugate. They're both acids. F is always going to be a base. Okay, H2O is, in this question, always a base, and H3O is always an acid. So you don't change whether you're an acid or base. You just slap on the word conjugate. Okay, who's the conjugate? It's just a matter of perspective. Okay, you can call the left side conjugates or you can call the right side conjugates. I don't care. Does that make sense? All right, so I have example 2 here, which is basically the same question as example 1, different compounds. So now you work on this. Tell me the conjugate acid-base pairs. I don't care if you look at it from the left or right. They're both right. The question is, though, wait, which one is the acid? Because they both have an H, so they both can be acids. So which one? So you have to figure that out. I'll give you like a minute or 2, and then I'll take this up. All right, so identify the conjugate acid-base pair. So first of all, you have to realize who's the acid right on the left side. You can't tell by looking at the left side, so you have to look to the right side. HSO3, what did it become? It became SO3. I mean, you lost that hydrogen, so you're the base. Sorry, you're the acid. Acid lose protons. HCO3, it became H2CO3, so you gained a proton, so you're the base. So now you realize that if you want to look at it from left to right, the SO3s, the HSO3 is the acid, the SO3 is the conjugate base. And the CO3s, well, if you have one H, you're the base because you gain one to become H2, CO3, which makes you the conjugate acid. And of course, you can look at it from right to left. You can have SO3 becoming HSO3. You gain a proton, that is a base. And then H2CO3, that is carbonic acid, you lose a proton to become HCO3, so acid and conjugate base. Doesn't matter which one you choose, they're equally right, so go ahead and pick one, all right? Any questions? Okay, so we're talking about acid and base equilibrium, which means we eventually have to talk about the K constant here. If you have this classic general equation for the equilibrium of an acid and water, well, HA with water become H3O and A minus, you can write the K expression. And this is exactly the same as the KEQ. Okay, we had KSP from solubility, same as KEQ. Now you have Ka, the acid ionization constant. Again, same as KEQ, except for acids only. It's product over reactants. Product being H3O and A minus, the conjugate base. Divided by reactants, you have the acid HA. Of course, you drop the water because it's a pure liquid. It does not count. All right, so you need to know how to write the Ka expression and also the Kb expression later. Same thing. You already know this. I'm just telling you that this applies to acid and it has a different name, Ka. You may have heard the words strong acid and strong base, weak acid and weak base used a lot by chemists. You have to know what they mean. Okay, a strong acid is an acid that ionizes 100% in water. Every single acid released a hydrogen and produced hydronium ions. Everyone reacted. There were no slackers. A weak acid kind of slacks off, right? Only partially ionizes. Only some of it is producing H3O. The other ones are just sitting there doing nothing. That is a weak acid. If you look at the picture, this illustrates the difference between a strong acid and a weak acid. The picture on the left, everything is ionized. You have a whole bunch of little white balls in the second beaker because they got released. But on figure B, the acids mostly stayed put. Only very few particles released their hydrogen, so that's weak. Here's what strong acid and weak acids are not. This is a common misconception. A lot of people believe that a strong acid is an acid with a low pH, and a weak acid is an acid with a high pH. Okay, that's what a lot of people believe. That's actually wrong. Let's say you have an acid with a pH of 0. That is extremely acidic. And let's say that you take battery acid from a car, sulfuric acid, pH of 0. Okay, yeah, that is a strong acid. But it doesn't mean it has to have a low pH. If you dump that into the ocean, what's the pH of the ocean? Still 7. All right, because that's not going to change anything. The ocean is too big, so you dilute it. You're still technically a strong acid. You have acid in there. It's so dilute, the pH is not very low. So a strong acid could have a low pH. Whereas another example, a weak acid, let's say vinegar, acetic acid, is a weak acid and only ionizes 5%. We can drink vinegar. Okay, that's an ingredient we use in food. But we can concentrate that, and it will have a very, very low pH to the extent that it becomes dangerous. If you can get a really, really concentrated vinegar, ethanoic acid or acetic acid, yeah, that will hurt. Okay, that will have a very, very low pH. So you can have a concentrated weak acid or a dilute strong acid. In this case, the weak acid will have a lower pH than a strong acid. It doesn't matter, you're still weak. What determines whether an acid is weak or strong is not the pH, it is whether they ionize. And the pH is dependent on the concentration of the acid, not whether it is strong and weak. Okay, the pH calculation is a little different for strong and weak acids, but it is the concentration that ultimately matters. Does that make sense? I was really naive a few years ago when I first started teaching. I was planning a chemistry lab for the students. It's the esterification lab. You had to mix ethanoic acid, which is acetic acid, which is vinegar, with ethanol, which is basically beer, the pure version of that. You mix them, you get an ester. We learned that in the second unit. So I was prepping that lab. I was going to do that beforehand to make sure it works, and so the concentrations work. So I left and I came back. Because I put them in beakers, I didn't label them. I forgot which one is which. I'm like, oh, that's easy. I'll just smell them because they have different smells. Like vinegar smells different from alcohol. And I knew that in chemistry, you're supposed to smell like this. You waft. I knew that. I was like, it's not really necessary though, because I know what they are. It's not like I'm smelling an ether here. It's just harmless alcohol and harmless vinegar, at least smell-wise. So, I'm just going to put my nose on it. Oh boy, a big mistake. I regretted it instantly. Okay, I happened to choose the one that is the acid. I smell, and no joke, for the next minute, I was screaming in the lab in pain. Because the acid was so concentrated, it was 99.9% acetic acid. And because it is so concentrated, and when I sniffed it into my nose, the acidity attacked my nose and it really hurt my sinus. I was actually in pain. And then after a minute, it subsided. I was like, okay, that's the acid. Don't do that again. All right, even though this is a weak acid vinegar, but at 99.9%, you don't want to mess with that. So the weak acid can be dangerous at high concentration. So that's not how you define a weak acid. Only the ionization. Okay, I hope I made that clear. Okay, so if you have a strong acid, and because we're talking about equilibrium, well, what about the equilibrium of a strong acid then? A strong acid is something that ionizes 100%. So this reaction goes to completion, 100% reacted. Does that make sense? All of your reactants were consumed to make 100% of products. That is not an equilibrium. This is a single error. If you want to calculate a Ka, which is the products divided by reactants, well, you can't. Because you're going to have to divide by 0. You have a lot of products, sure, 100% of the products. 0 reactants, and when you try to calculate Ka, you divide by 0, that doesn't work. And if it is not 0, maybe you have a little bit left. And that is going to be a huge, huge number. That approaches infinity. Because the smaller number you divide, the larger the result is. So Ka of a strong acid is just so large, we don't really talk about that. We say that it doesn't have Ka. It's a strong acid. There's no equilibrium. It's a one-way reaction. So there are 6 known strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. So 6. Only those are strong acids. The rest of the acids in this world are weak acids. And amongst those strong acids, they're equally strong. Okay, no one strong acid is stronger than another one because they all 100% ionize in solution, so they're equally strong. They produce the same amount of H3O at the same concentration. So that's a strong acid. No equilibrium, one way, 100% ionized, and extremely large Ka that is so big we don't really use the Ka anymore. And there's only 6 of them. You don't have to memorize the 6. You have a data booklet. In the data booklet I gave you, one of the pages is the Ka table. All right. On the Ka table, the first 6 are the 6 strong acids. And you can see that on the right side, the Ka says very large. It doesn't really tell you. And then below that, you have the weak acids, which do have Ka. So these 6, just refer to the table. You see them, strong acid. Now, weak acids is in equilibrium, okay? Because you only partially reacted. Let's say 5%. Normally, a weak acid reacts like 5% of the time. Only 5% reacted, so you have an equilibrium.
Most of the HA are unionized. They didn't ionize. So you produce very low concentrations of H3O. That's why we call it weak. And they have low Ka. If you have a low K value, we learned in the equilibrium section, if you have a low K value, that means the equilibrium favors the reactants heavily. At equilibrium, most of your stuff is still reactants. Very few of them reacted to become the product. So all weak acids have low Ka. All right, so, but you can have lower Ka and higher Ka amongst weak acids. So they're not all equally weak. Some acids are weaker than others in weak acids. And if you compare between the weak acid, if you have a larger Ka, that means you're stronger. Okay, you produce more H3O at equilibrium, so thus you're stronger because you have a lower pH. Does that make sense? So you compare Kas amongst weak acid. High Ka means more acidic. Small Ka means less acidic. And that's how you calculate Ka. We talked about this already. So these are weak acids. They're at equilibrium. They have a Ka value that is quite small. Right? And they don't 100% ionize. Usually, the equilibrium favors heavily the reactions, not the products. All right, so imagine a weak acid equilibrium. Can you put a weak acid in water? This is like a competition for protons. It's like they're both competing to see who's the better acid. You see what I'm saying? HA will try to donate a proton to water. And once water takes that proton, it's like, wait a minute, I'm an acid too. I'm H3O now, so I'm going to give this back. It's like, you take this proton. Oh, no, you take this proton. No, you take this proton. They're both trying to get rid of the proton. It's like a soccer game where they try to kick the ball into each other's nets. No, you take the ball. No, you take the ball. Okay? And just like a soccer match, one side is typically stronger than the other side. When I watch soccer, the result is usually 0-0, which pisses me off, but a lot of time it's not. One side does win. And in weak acid competition, one side wins. The HA is trying to give the H to the water, you're an acid, but once you get the proton, you become the conjugate acid. All right, H3O is now the conjugate acid, so now you are acidic. You will then try to get rid of the H3, the hydrogen, by giving it back to the conjugate base, A minus. Right, so I literally want to give it back to you. So who's better at giving the proton will dictate who is the acid. You see what I mean? It will dictate the equilibrium. Imagine that I'm trying to kick this ball into your net, and I'm very good at this. And you're trying to kick the ball back into my net, but you suck. Who's going to win? You see, one side is going to score more goals than the other side, so that side is going to be the winner. So the equilibrium will favor the side with the weaker acid. If you suck at giving protons, then you're going to get a lot of protons in return. And because of that, you're going to have high concentrations of the protonated version. You will have more reactants in this case. If HA suck at giving the hydrogen away, you're going to have a lot of HA left. Okay, does that make sense? So the equilibrium will have a lot of those. It will favor the weaker acid, the side that is less capable of donating protons. And the stronger your acid, the weaker is conjugate base. If you're really good at donating proton, then you probably suck at taking protons. Okay? Because if you're good at taking protons, you can't be good at giving that away. You can pick one. Okay, so if you are a weak acid, you suck at giving away protons, well, then you're going to get a lot of protons. See, the weaker the acid, the stronger the conjugate base that it makes. And the stronger the acid, the weaker its conjugate base. It's an inverse relationship. And on this table, this is your Ka table from your data booklet. On top, you have the 6 strong acids. In no particular order, they all have a very large Ka. But starting from there, you have hydronium that has a Ka of 1 by definition, and then you go down. When you go down, it's a descending list. Okay, the one nearer to the top has higher Ka. So the ones closer to the top are stronger acids, and the ones closer to the bottom are weaker acids. So therefore, if you look at their conjugate base, the one near the top are strong conjugate bases. Well, stronger, relatively speaking. And the one on the bottom, sorry, I messed up. The one on the top are the weakest conjugate base because they have the strongest conjugate acid. The one on the bottom have the strongest weak bases because they have weak acids. Did I make that clear? If you're a weak acid, your conjugate base would be strong. Again, by strong, I mean for a weak base, you're strong. You're not a strong base. You're a relatively strong weak base. If you're a really strong, quote unquote, weak acid, you have a high Ka value, then your conjugate base is going to be very, very weak. Always an inverse relationship. Okay, so that's how you look at this table. There are two columns, one for the acid, and then the column beside it is what it will become as the conjugate base. And then you have the Ka of the acid. Okay, it's in descending order. All right, so what about strong and weak bases? It's the same idea. If you know about strong acid and weak acid, you should know about strong base and weak base. A base will dissociate in water to make hydroxide, right? That's the definition we learned with Arrhenius. If you're a strong base, you will do this 100%. You will produce 100% hydroxides. If you're a weak base, you will only partially produce hydroxide, just like a weak acid. So if you look at the picture here, a strong base, sodium hydroxide, boom, you drop that in, 100% dissociation. Weak base, NH3, you drop that in water, only some of them become NH4. A lot of them just has no change. That's a weak base. With a strong base, it is a one-way reaction. Because you're 100% ionized, you don't go back. Okay, so that is not an equilibrium. The hydroxides of group 1 elements, like lithium, sodium, potassium, rubidium, cesium hydroxide, they're all strong bases. They will 100% ionize, and you're going to get a lot of hydroxides. The group 2 alkaline earth, they're also strong bases. They will 100% ionize and give you a lot of hydroxides, so they're strong base. All right, do we have any questions? Really? I'm expecting a very specific question here. Nobody sees something perhaps confusing? Oh, well, okay. I'm going to answer your unasked question anyway, because I know eventually. Okay, please ask if you have a question.
Why is there no magnesium in the second group?
Oh, no, I just didn't happen to write it. I think I just left that out. But yeah, no, magnesium should be there. Okay. That's it? That's not the question I was expecting. All right, so we just learned about solubility, right? We just had a test on solubility. Calcium hydroxide. Is that soluble? If you look on the data booklet, it says slightly soluble, not really. What does it mean by slightly soluble then? Well, it is in equilibrium with the solid. So it's not 100% reactant. So how come now I'm saying that this is a 100% reaction? Right? You see, is there a conflict? No. There is no conflict. The solubility unit, we talk about calcium hydroxide solid dissolving in water. That is an equilibrium because you don't really dissolve well. You reached saturation. If you don't reach saturation, that is a one-way reaction. Okay, if you already have aqueous calcium hydroxide, it will 100% break apart to make calcium 2+ and hydroxide.
if you already dissolve. If you didn't dissolve, that's a different story, but that's not what we're saying here. We're saying that of the dissolved calcium hydroxide, okay, you suck at dissolving, but you will dissolve to some extent. The ones that do dissolve, that is 100% dissociation. So there is no conflict. This is talking about breaking into ions after you dissolve, and this is 100%. That's what makes it a strong base. Okay, so they are in fact strong bases. The rule of thumb, if you see OH, it's probably a strong base. Rule of thumb, not a law. Okay, most of the time. You good? All right, so what about weak bases? Ammonia is our classic example of a weak base. It doesn't have a hydroxide. It doesn't need one. It will make one. So ammonia will produce hydroxide by accepting proton from water. Okay, it becomes protonated. If you get a proton, that's protonation. But this happens at a low percentage. It's an equilibrium. The equilibrium lies on the left side. It favors the reactants. Okay, so at equilibrium, you have very few products, and you still have some. It's just very low concentration. So most of the NH3 are unprotonated. They didn't receive a proton. So you produce very little hydroxide. That's why it's a weak base. It's equilibrium. Okay, it's the same idea as weak acids. And you could write the Kb expression for the ionization of a base, or the protonation of a base, I should say. You have a base in water, the base should get protonated, the water donates a proton, water becomes OH, base becomes BH. You write the base ionization constant expression. Products of a reactant, you have OH times the conjugate acid, BH plus, divided by your base. You ignore liquid water because it's not aqueous or a gas. All right, and if you have a large Kb, if you're a strong base, you will have a very large Kb. It is so big, it approaches infinity. We don't really consider that. And for a weak base, the larger the Kb, the stronger the weak base compared to the weak base with a smaller Kb. So basically, it's the same as the acid, except replace A with B. All right, so last example for this class. Write the Ka or Kb expression for the two equilibria below. I'm not going to tell you which one is acid, which one is base. You figure that out yourself. Look, it's the same compound, HCO3 for both, with water. So figure out which one is acid, which one is base, and write the Ka or the Kb expression. I'll take this up in like 1 to 2 minutes. All right, which one is the acid? Which one is the base? You can answer this question by looking at the products. HCO3 and water, what did it make? Oh, look, the water became OH. So you made a base. HCO3 took a proton from water. That is the action of a base. So that is a basic reaction. And therefore, you would have a Kb. This is base in water and products over reactants. Make sense? One on the bottom, you make H3O. Okay, water, H2O, becomes H3O. That means you donated a proton to the water. If you donate a proton, you're an acid. So you use the Ka expression. And that's the answer. A base has a Kb value. An acid has a Ka value. Don't get them mixed up. An acid does not have a Kb value. Kb only applies to bases, and Ka only applies for acids. If you have a base, you're not going to get a Ka for that base. You don't get them mixed up. All right, so that's the end of this lesson. We learned about we reviewed the Arrhenius theory, and then we learned about the Bronsted-Lowry theory of an acid base, proton donor, proton acceptor. We learned about Ka and Kb. We learned about conjugate acid-base pair. We learned what a strong acid is. We learned what a weak acid is. And we learned the equilibrium for both Ka and Kb. Okay. Do we have any questions? All right, awesome. I'm going to end this.